In this video, we're going to talk about logarithms. Logarithms can be used to measure noise levels in decibels. It can be used to measure the pH in chemicals. You can use it to find half-life in radioactive materials, or you may use logarithms in your math classes. Whether you're studying physics, chemistry, or finance, logarithms are a useful tool in your day-to-day life. Logarithms are related to exponentials. If you have a logarithm, like log to the base b of x, and say that's equal to some number, m, this is equal to, say if you'd have b to the m power is equal to x. Let's run through the 7 common rules of logarithms, and we'll do examples for each. There's chapters in this video, so if you want to look for a certain rule, just find that chapter. This is the identity rule. It states that if your base is the same as your variable here, it's going to equal 1. So if you have, say, log base 3, and your variable is 3, the answer is going to be 1. Just a second ago, I said that logarithms are related to exponentials. We have our base of 3 raised to the m power. That's going to equal 3, and that checks out. Next, we have the 0 rule, which states that if you have a log to any base of 1, you're going to get 0. So say we have log base 9 of 1, that's going to give us 0. And if we transfer this into an exponential form, we take our base 9. This number here, this would be our exponent to the 0 power. And anything to the 0 power is 1. So that's the 0 rule. Pretty easy, checks out. Next, we have the power rule. Say we have log to some base x, and then our variable is raised to some power k. We can bring this exponent to the front of the entire thing. So we're just left with k times log base x of a. How can we prove that? Let's prove it simply by saying we have some number m is equal to log base x of a. Now let's rewrite that as an exponential equation where we have a is equal to x to the m power. Now let's raise both sides to the power k so that we get a to the k power is equal to x to the m k power. Next, let's perform logarithms with base x, and we'll apply it to both sides of the equation. So if we have log base x, ak is equal to log base x of x to the mk, we can simplify this side by using the inverse property for logarithms, which states if we have a logarithm of some base and we're performing that logarithm to some variable of the same value as the base, this gives us just the exponent of that variable. So this simplifies to log base x of ak set equal to just mk. Now we know the value of m. The value of m is log base x of a. So we can fill in that variable, and there we have the proof for the power rule. We got exactly what we had up here. Next, we have the product rule. This states that if we have a log of some base of two variables that are being multiplied together, we can break that up into two separate logarithms for each of the variable and then add that together. Let's go ahead and prove that. So let's say we have some number m is equal to log of base x of a, and then we'll have some number n set equal to log base x of some number b. Let's go ahead and transfer each one of these to its equivalent exponential function. So for this we'll have x to the m power is going to be equal to a, and x to the n power will be equal to b. So since we're proving the product property, we'll multiply a by b. So we can rewrite this as a times b is equal to x to the m power times x to the n power, or x to the m plus n power. Because when you're multiplying two numbers, each raised to an exponent, you add the exponents together. Now let's take the logarithm of both sides of the equation, and we'll use the inverse property of logarithms like we did proving the previous rule. That states that log of some base x of a variable x to some power a will simply be equal to a. So continuing on, we'll perform logarithms on both sides of this equation. So we'll have log of base x of ab equal to log of base x of x to the m plus n power. And this gives us log base x of a times b is equal to m plus n. And we have our values for m and n up here. So filling it out, we have log of base x of a times b is equal to log base x of a plus log base x of b, just like we have up here. So there we go, we just proved the product rule for logarithms. Now let's prove the quotient rule for logarithms. So this one's similar to the product rule, except we have log base x with our a variable divided by our b variable. That's just going to be equal to log base x a minus log base of x of b. Now in proving it, let's say that we have some number m that's equal to log base x of a, and we'll have some number n is equal to log base x of b. Now, just like before, we'll express each of these in its equivalent exponential equation, where we have x raised to the m power is a and x raised to the n power is b. Now let's divide a by b, which gives us x to the m power being over x to the n power. And this is if you know how to divide numbers with exponents. You'll know that this is just going to be x to the m minus n power. Now let's go ahead and apply a log of base x to both sides. And again, using the inverse property for logarithms, this is just going to be log base x of a over b is equal to m minus n. And we have our m and n values. So if we fill those in, we get our quotient rule. So that's our proof for the quotient rule for logarithms. Now let's look at the change of base property for logarithms, where we have log of some base b of a is equal to log base c of a over log base c of b. Let's let our log of base b of a equal k. We'll set it to k. And now we'll express this as its equivalent exponential equation, where we have a is equal to b to the k power. Now let's apply logarithms with a different base to both sides of the equation. Let's do log of base x of a set equal to log of base x of b to the k power. Now we'll apply the power rule to the right side of the equation, and we went over the power rule earlier in the video, where we can just bring this exponent out to the front of the logarithm. So we're going to get log base x of a is equal to k times log of base x of b. Now we can solve for k by dividing both sides by log base x b. So we get log base x of a over log base x of b is equal to k. And we have our k value up here. So filling in our k value, we are left with this, which is basically what we have up here. So there's our proof for the change of base property for logarithms. Let's go over two more quick properties for logarithms before we get into the examples. So this is the inverse property of logarithms. We used it a few times in proving some of the other rules for logarithms. States that you have a logarithm of some base x of some number that's the same value as the base raised to a exponent. Your final answer is going to be that exponent. Another one to keep in mind is the inverse property of exponents, where raising the logarithm of a number to its base, it's equal to that number. All right, now let's get into the examples. So we went over all the proofs, we went over all the rules and properties of logarithms. And if you skipped ahead to this point, if you get stuck or you don't know what I'm doing in one of these examples, I suggest you go back and look at the explanation of the rules so that you know what's going on. So let's say we have log base 2 of 8 plus log base 2 of 4. Now we can simplify this by expressing the 8 and the 4 as numbers with a base of 2. We can see that both 8 and 4 can be expressed as exponentials of 2, where we would have log base 2 of 2 to the third power, because 2 to the third power is equal to 8, plus log base 2 of 2 to the second power, because 2 to the second power is 4. Now we can apply the power rule, where we simply take the exponent and place it in front of the logarithm. So this is going to give us 3 times log base 2 of 2 plus 2 times log base 2 of 2. Now we can apply the identity rule, where we have our base is the same as the number we are taking the logarithm of. When these two numbers are equal, this is just equal to 1. So this gives us 3 times 1 plus 2 times 1, and that gives us 5. 5, that's our final answer. Now let's say we have log of base 3 of 162 minus log base 3 of 2. So we're not going to be able to express 162 as an exponential number with base 3. you can't raise 3 to any power to give you 162 as your answer. We're going to need to take a different approach. What we can do is remember the quotient rule. Because we have two logarithms being subtracted, we can use the quotient rule in this manner. So we can rewrite this as log of base 3 of 162 over 2. That gives us log base 3 of 81. Now we can express 81 as a exponent with base 3. So 81 is just going to be 3 to the 4th power. 3 to the 4th power is equal to 81. Now we can simply use the power rule, bring our exponent out in front, giving us 4 times log base 3 of 3. Then using the identity law, we know that log base 3 of 3 is just 1. So our final answer is going to be 4. Here's an example. It's a little bit more of a tricky one. We can see that we have two different bases involved here. If you want to try this one out for yourself, go ahead and pause the video and see if you can work it out using the rules and the properties we went over previously. So we see that we have two different bases. We have base 5 and base 4. We also see that the base 5s are being subtracted and the base 4s are being added. So what we can do is we can use the quotient rule on this side and the product rule on this side. Then we can get our final answer by adding the two values. So first off, let's use the power rule in reverse here. Let's take this 2 and put it back into this 2. That's going to give us log base 5 2 to the 2nd power, which is 4. Now let's use our quotient rule and we'll express this half here as log base 5 of 500 over 4. And here we'll use the product rule in reverse. That's going to give us log base 4 of 32 times 8. We can simplify as log base 5 of 125 plus log base 4 of 256. Now, can 125 be written as an exponent of base 5? Sure, that's going to be log base 5 of 5 to the 3rd power. Now what about here? Can 256 be written as an exponent of base 4? Yeah, it can be written as 4 to the 4th power. 4 to the 4th power is 256. Now we can use our power rule, bringing our exponents to the front of each of the logarithms. That gives us 3 times log base 5 of 5 plus 4 times log base 4 of 4. Now using our identity rule, these two numbers are the same, so they can be just 1. Same for over here. The base is the same as our variable, so the entire logarithm is equal to 1. Now we're just left with 3 plus 4, and that gives us 7. So this whole thing is just a fancy way of saying 7. I think that's it for today. We went over the rules and properties for logarithms. We showed the proofs for the product rule, the quotient rule, the power rule, and the change of base. We did a couple of examples. I encourage you to keep trying, keep practicing. Logarithms do get really tricky and kind of confusing. So keep sharpening your skills, and thank you for watching.